All right, come on in, come on in. We're on and roll. All right. Well, good morning. I'm glad you guys are here. It is time for our class to get started, so let's stand for prayer and let us remember that we're in the holy presence of God. All right. Heavenly Father, we thank you for this day. We thank you for the blessing of this life, for the opportunity that we have to continue our work here at school, and God, for the beautiful weather you've blessed us with this time of year especially. We thank you for our schools and for the hard work that they are putting in to keep us safe and healthy. And Lord, we pray that you bless those of our student body, those of our faculty, those of our school communities who might be sick right now. Please bless them, let them get better. And God, I pray that you would continue to watch over our town, our state, our country, as not only we elect new leaders, God, but we also strive to fight this pandemic and get through this tough time. God, we know that we can do all things through you who give us strength, and pray that we can lay at your feet all our cares and worries. Lord, we thank you for Christ and for his love for us, and may we be a light shining in this world today. We ask this all through his holy name. Amen. St. John Baptist de La Salle, and let Jesus in our hearts. All right, y'all have a seat. Get your notes out if you don't have them out already. You guys that are online, you've seen the screen for a few minutes now. And what we're going to do today is we're going to actually kind of tag team a lesson or two, depends on how far we get. But we've been talking about systems of equations, right? Systems of equations are where you just group a couple of equations, 2, 3, 4 equations, however many you want, group them together. We talked about what it means to solve a system. It means to find all the points of intersection between the graphs of those. So like, for example, if I had, a system of equations where one graph looked like this red line and another graph looked like this green parabola, there would be two solutions to that system because there's 2 points of intersection. So that's kind of our job, is we're looking for where are all those points that make a true statement when their coordinates are plugged in, not just to the first equation, but also to the second or third or however many other equations we've got. The text will take us through, and goodness knows I don't want you guys to write all these steps down, but the text will take us through and it will kind of slow play and explain, here's how you solve this system using graphing. I'm going to give you the gist of it, okay? You graph the first line, you graph the second line, and see where the daggum intersect, okay? It ain't that hard. Now, we talked, what's today, Thursday? We talked on Tuesday about, there's a couple of sort of what you might call special cases. You'll remember that we said in one of those special cases, the lines are parallel. They actually don't intersect. So what would our, quote, solution be for that one? Yeah, we'd say no solution. We'd say, sorry, Charlie, there ain't a line, or rather a point where those two lines cross. And in the third case, our other little special case there, we said those lines coincide. They're actually the same line. So we'll see an example like that today too. We say that's where there's infinitely many solutions, okay? But the vast majority of our problems are going to look just like example 3. So that's where I'd like us to start today, okay? So in your notes, write that system down, and I'm going to walk you through what my recommendations are for how to solve a system by graphing. And I'll be honest with you, this is not the most reliable method. We'll learn a little bit later on a method called substitution. We'll probably introduce that today. It's way more reliable, okay? But graphing has its benefits in that we get a visual idea of what that solution might be, okay? Now, little recommendation, little kind of older brother advice, fatherly advice, teacherly advice, whatever you want to call it. If I were you, I would get y by itself in both of the equations. That's the first thing that I would do if I were you guys. Grove, help me do that on this first equation here in blue. What do you want to do to get y by itself?
Subtract 2x by both sides.
Very good. So we're going to have y equals negative 2x plus 7. And notice when he said subtract 2x from both sides, I didn't write it 7 minus 2x. Why not? Why didn't I say y equals 7 minus 2x? Yeah, because y equals mx plus b, where m is the slope and b is the, we remember? The y-intercept. Good. Y'all had to think about it for a sec. Okay, so check this out. Here's what we've got now. We've got a y-intercept of 7. That's our yint, the y-intercept. And we got a slope right here of negative 2 over 1. So by doing my recommendation of getting y by itself, right now we can graph this line with great success. We can go up 7 on the y-axis, 4, 5, 6, 7, and we can put our dot there. That's our starting point. And then the slope of negative 2 means I go down 2 and to the right 1. Down 2 and to the right 1. That's exactly what I intend to do here. So down 2 to the right 1, down 2 to the right 1. My tick marks are not very well spaced apart here, so forgive me. There we go. All right. So that's our first line, right? That's easy. Let's do the same thing for the second line. What did I say we want to try and get by itself? We want to try and get y by itself. All right. So let's do that over here. What do you think? Subtract x from both sides. So we got negative 2y equals negative x plus 6. And then I want to divide everything by negative 2. Divide, divide, divide. And that becomes y equals 1/2 x minus 3. So this orange line, he has a slope of 1/2. Slope is 1/2. Y-intercept, good old yint, is negative 3. So that means on my graph, I'm going to start at y equals negative 3 on that y-axis. And my slope, I'm going to go up 1 and over to the right 2, up 1 and over to the right 2. And then I'm going to connect those dots. Now, what are we looking for here, Nate? What am I trying to find on this graph? Yeah, I'm trying to find where do these two lines cross. And it looks like they cross right down here at the point 4, negative 1. I say it looks like that because looks can be deceiving. Therefore, I want to check. I want to make sure. I want to test it out. And this is what we did on Tuesday. I want to check to make sure that 4, negative 1 is the solution. So I ought Jack Candiato to be able to plug it in and get a what? I ought to be able to get a true statement in both lines. Okay? So, and actually plugging and chugging at this point, you guys are smart enough to do it in your head, use your eyes. So y'all help me. Look at that first line right there. We got 2x plus y equals 7. Let's let x be 4 and y be negative 1, our supposed solution. If I plug in x equals 4, that gives me 8 on that first term. If I plug in y equals negative 1, that gives me negative 1 on that second term. 8 and negative 1, they do tally up to equal 7. So check. We got a true statement. That means that that point 4, negative 1 is on the blue line because it gave me a true statement in that first equation. Okay. On the orange line, I plug in its coordinates, 4 for x and negative 1 for y. 4 on the first term. Negative 2 times negative 1 is positive 2, so 4 and positive 2 makes 6. I get a true statement on the second equation as well. So that means that point is on the, the orange line as well. Therefore, it's the point of intersection, and it is, in fact, our, quote, solution to this system. It's exactly what we just found. We found the point that makes a true statement in both equations. Any questions on example 3? Is that pretty straightforward? No pun intended? You guys do one on your own. I'm going to mosey around through the classroom and see what you guys are doing. Work it the exact same way. We want to graph out both lines, but first it'd probably be a good idea to get y by itself in both those lines. Now, I don't know if you guys typically follow along on deltamath.com, these homework assignments that I post. Pretty much every time I give a homework assignment to my ninth graders, I give it to you as well. And although I don't have like a grade book that I'm keeping for you guys, I do expect you to be practicing along. So like, for example, with this material, which y'all are working on right now, you'll see there's 15 problems on the Delta Math homework assignment 4.1 is due at 3 p.m. today, but really just, you guys get it done when you can. It'll look like exactly like this. It'll give you 2 lines and it'll say, hey, graph this line. And of course, with it being a computer program, what you'll do is you'll put a point down on the y-axis and then you'll find your slope and you'll go up and over or down and to the right or whatever. And you'll plot your second point and then you'll just do that for both lines. And then you'll say, where do they cross? Where do they cross? And that's the job we have here before us. Now, as I've walked around, I've seen quite a few of you guys do the following. Before you did any work, you put down, this big fancy looking XY plane. And I mean, you had 10 tick marks to the right and 10 tick marks to the left and 10 tick marks up and 10 tick marks down. Don't do that. Don't do that. That's going to waste your time and mine. What we want to do is we want to first get an idea. Did you notice in the last example, like how many tick marks did I go up? I went up 7 tick marks on the y-axis. I didn't even go any tick marks to the left because the majority of my graph was over there to the right, okay? So when we consider making our plan, our XY plane, don't just make a bunch of random tick marks. Use tick marks where you need them and save yourself a little bit of time. But we do want those tick marks to be equally spaced. I did a lousy job of that in the first example. So try and, you don't have to get graph paper or whatever, but do try and be a little bit more precise than I was. All right, let's see here. Mossy, what did you do to get y by itself on this first equation? So y equals negative 3x minus 1. Again, put that y term, or excuse me, that x term first, okay? Joey, what'd you do on the second one to get y by itself? So we got y equals negative 2x. Technically, it's negative 2x plus 0. Nobody ever writes the plus 0, but I'm going to put it there just to illustrate that that's our what? 0 is our y-intercept. Very good, very good. All right, so now if I look at my graph, I mean, it looks pretty much like all I need is the one tick there on the y-axis and then a slope of negative 3. So I'm going to go down 3, 1, 2, 3, and to the right 1. And I've kind of run out of room here. I do like 3 points. So Tiago, instead of going down and to the right, where else could I go?
Up and to the left.
Very good. I could go up and to the left. There we go. It's hard to draw straight lines on this goofy, with this goofy stylus here, but all right, there we go. All right, my orange line, it's got a y-intercept of 0, and it's got a slope of negative 2, so I'm gonna go down 2 and to the right 1, down 2 and to the right 1 more. Looks like that is my orange line. And I have a sneaky suspicion that this point right up here of negative 1, comma 2 is my solution. It certainly follows suit that my slope would have me go, if as like Tiago said, I could go up 2 into the left 1, I would get there again. And in fact, that is the case. I don't know if you guys had time to plug and chug, but you'll get a true statement in both. That is our solution. That's our point of intersection. Now, those 2 lines were a little bit close together, weren't they? They were kind of hard to distinguish if we had a real small graph. If I had done like just a little teeny tiny graph, it would have been hard to figure out, well, where do they cross? So this is a good lesson for us. Give yourself some space when you're graphing. Don't try to just cram it all into like a little 1-inch square. Give yourself a little bit of space. Whole daggum piece of paper, but do be patient with yourself and give yourself some room. Any questions on example 4? You guys have done a couple of these now. Anything you'd like to ask at home or here in person? All right. Y'all feel pretty comfy with graphing lines just in general, getting y by itself and realizing what the slope and the y-intercept are? Okay. Will your y-intercept always be a nice, neat little integer? No, but that's okay. We can deal with those in-betweeners. Okay. All right, here we go. Here's a special case. This is one of those two. It's either going to be the parallel lines or the lines that coincide. We know it's going to either be infinitely many solutions or no solution at all. Let's take this second line right here. Let's get y by itself. Okay. So it's going to take 2 steps. Andrew, what are my 2 steps? Get y by itself in that second one. Ooh. Ooh. Goo. What did we do first on these 2? We subtracted the x term. What did we do first on these 2? We subtracted the s term. Hey, make a note of that, fellas. The first thing you want to do when you're taking an equation out of standard form, please do not divide, okay? That's like the old thing I talk about Shrek, and an ogre has layers like an onion. Start on the outer layer. Get rid of that x term first. So, Andrew, what do we want to do to both sides? Very good. So we're going to subtract x from both sides. We're going to list it first before that constant. All right, and then you can go ahead and divide by -2. So y equals, now look, if you don't write it out, sometimes you can get confused. So I'm going to write it out just to make sure. We got 1/2 x minus 2. Now looking at this line and that line, our first line and our second line, we got y equals 1/2 x minus 3 and y equals 1/2 x minus 2. George, what do you notice about those 2 lines? What do they have in common, in other words? Their slope is the same, and they have different y-intercepts. So graphically speaking, when that's the case, fellas, looky, here we go. There's the y-intercept of -3, and it's got a slope of 1/2. There's the first line. Here's the second line, y-intercept of -2 and a slope of 1/2. What do we know about lines that have the same slope? They are parallel when they have the same slope and different y-intercepts. And it's an inconsistent, I like how somebody used that vocab word, it's an inconsistent system. So we would say, there is no point of intersection. You know, sorry, out of luck. No point that when I plug his coordinates in would give me a true statement in both equations. Now there's plenty of points where I could plug the coordinates in and get a true statement in one of the equations, but those points would just be on one of the lines, not on both of the lines. So we call that an inconsistent system. No solution. And then our last example here in this lesson is very similar. We get y by itself here in that second equation. We're going to do the same 2 things that Andrew told us. Jack McVie, what are those 2 things going to be? All right, so we're going to add 6x to both sides. He's using that inverse operation. It was negative on the left, so now it's positive on the right. And then last step would be? Divide everything by 3. So that's going to be 2x minus 3. And then I want to compare. And what do I notice here? Yeah, they're exactly the same thing. It's a dependent system. They have infinitely many points in common with one another. So like if I graph this one out, 1, 2, 3, go up 2, there we go, up 2 over 1. There's my first line, and there's my second line. Okay, it's real trivial. There's infinitely many points of intersection, so we'd say there's infinitely many solutions. Because, as James said, it's a dependent system. Right, your solution just depends on where you want to look on the line. So that's a trivial example, right? You won't run across very many of those, but we do want to understand how that works, okay? So sometimes there are those 2 systems where there's either no solution or infinitely many, but the vast majority of the problems that you guys encounter are going to look like example 4 and example 3. Okay? That's graphing in a nutshell. It's very straightforward, but it's a little bit what? Time consuming. We got to put down a daggum XY axis. We got to figure out what the intercept is and plot this and cross that, and then we got to double check it to begin with, or rather to end with. So what we're going to search for today is we're going to search for a better way, okay? And actually, I like this example that I've got on the screen, so I'm going to pitch it to you using this example, okay? We want a better way, a way that's a little bit more reliable, right? Because I hate to say it, but my graphs aren't always the most accurate, are they? And one that's a little bit more, a little bit less time consuming. So this is going to be a method called substitution, okay? If I could get my screen to cooperate. Here we go. Now, I'm dressed up a little fancy today because I got to go to a funeral later on this afternoon. And so I set up a what to take my place in class for my afternoon classes? A substitute teacher, right? So I sent in my sub request. That teacher is going to come in and replace me and do the same job that I'm going to do. Teach those 7th and 8th period guys some math, right? And so substitution, we've talked before about how that's like kind of just plugging and chugging. The principle of substitution is where I'm going to say this and that are equal. So wherever I see this, I can erase and I can put that because they're the same thing. Okay. Now, I'm going to give you a nice little step-by approach. Okay. Here's your first step. We got this system. We know the solution. What was it, like 4, -1, something like that? Right? So we know the answer we're supposed to get. This is a good example to use. The first step we're going to do is to pick a variable in one of the equations to isolate. Okay, so pick a variable to isolate. Pick a variable to isolate. That means get by itself, right? Now, again, give you a little teacherly advice here. I would pick, write this down, I would pick, if there is one, I would pick one with a coefficient of 1. Okay? It's easier to get something by itself, to isolate it, if it doesn't have, a coefficient written up there already. So like, for example, Drew, could you tell me which variable might be easier for me to isolate in the first equation? Okay, what about the second equation? X, okay, that makes less work for us. So we want to pick a variable to isolate. It really does not matter which variable you pick, but if you want to save a little bit of time, then pick the one that's got a coefficient of 1. That's my recommendation. So because we solved for y already in the other example that we worked, why don't we get x by itself in the second equation here? Okay, so what's that's going to look like is x equals 2y plus 6. Just added 2y to both sides, right? Savvy? All right, now I want to use, it's called substitution. I want to use that analogy, okay? So Coach Morgan has got to go to a funeral. Coach Morgan is X, okay? He calls in, he says, hey, I need a sub. Who's going to take his place? 2y plus 6. 2y plus 6 is going to come in. So wherever I see Coach Morgan, wherever I see an X, I can plug in a what? A 2y plus 6. That's the substitution. Okay, so step 2, check this out. Step 2 is we're going to sub that expression into, watch this now, the other equation. And I underline the word other because that is muy importante, as they would say in Espanol. Okay, that's very important. Okay, because watch what happens if I try plugging this expression back in to the equation from which it came. Okay, so like if I took this this second equation and instead of x, if I wrote 2y plus 6 in place of x, right? It was x minus 2y equals 6, and I just said, let's take out the x and let's put in what we subbed it in, 2y plus 6. What am I going to get right here? I got 2y plus 6 minus 2y equals 6. What happens to the two y's? They cancel each other out. They're like terms. I got 6 equals 6. Well, duh, that's like a dog chasing his tail. We're not going anywhere. So if you try plugging it into the same equation from which it came, you're not going to get anywhere. That's a bad idea. But check this out. If we plug it into the other equation, okay, watch what happens. If we plug it into the other equation, instead of 2x plus y equals 7, we're going to do 2 times 2y plus 6. Okay, now we're cooking. Now we're cooking. Can you guys help me simplify some things out? What property, Will Edwards, should I use to start with?
Distribution.
Very good. We're going to do the distributive property for y plus 12. And then we want to combine some like terms, don't we? Okay, Alex, combine some like terms. So we got 5y plus 12. Can we subtract 12 from both sides, you guys? And divide both sides by y, or excuse me, by 5. And we get negative 1. Now, James, is that the answer to my problem? Am I finished, in other words? Say no. No, heck no, Coach Moore, you're not done. Because I want you to remind me, fellas, what does it mean to solve a system, to find the ordered pair? We've only got half the answer. So our third and final step is to use that number to find the other variable. Use that number to find the other variable. When I say use that number, just take y equals negative 1 now and plug it back into wherever you see a y value. Now, again, little teacherly advice. Yes, you could plug it into either of the black equations up there, or you could be smart and you could say, you know what? Coach Morgan, we already solved for x, which is what we're looking for still. We've already solved for x over here. Why don't we plug in y right here? How now, brown cow? Because then I've got no more work to do as far as isolating x. If I plug in negative 1 right here, okay, my work is done. All I got to do is combine like terms, do a little arithmetic. So if you take that with me here, we got 2 times negative 1 plus 6. Okay, what's 2 times negative 1? That's negative 2 plus 6. So x equals what? X equals 4. And of course, how do we answer a system? We give it in an ordered pair for negative 1, and then look at that. Ooh, yeah. So that's substitution in a nutshell, fellas. That's a 3-step process. Pick a variable, get it by itself, plug that expression into the other equation, solving for, that variable, that number, and then take that number and plug it into the any of the equations, but smartly you can plug it into the one where you've already got it solved for. And that will help you find your answer in a more reliable way. Okay, so like we had 4, negative 1 was our answer, but this way, and you might say, well, dadgummit, that didn't take any less time than the graphing, coach. Well, that's true initially, but once you get a little faster at it, okay, the graphing is still going to take however long the graphing takes, but the substitution, you'll become more efficient at it. You'll get quicker at it. Plus, where graphing might let me down, like graphing might let me down in a scenario where there's, like let's just make a couple of tick marks here and here. And like, let's say that this is one line and this is another line. How in the heck am I supposed to figure out where that point of intersection is? You know what I mean? So like graphing has its limitations. I could guess, I could ballpark, I could say maybe that's like, 1.5 comma 0.25, but I wouldn't know with certainty unless I did the algebraic approach of substitution. So graphing has its limitations. Substitution is the bee's knees. It's the cat's meow, okay? We want to be good at substitution. Can I give you one to work on? All right, good. Well, y'all hold your horses just for a sec. There's your example. I'd like y'all to try that. And remember the piece of advice that I offered, Drew Benton was helping me with this. The first step, pick a variable to get by itself. If you can, pick the one that doesn't have a coefficient sitting in front of it. That makes life a little bit easier, okay? Makes life a little bit easier. Oops, where did I go? Sorry about that. Ah. Hold on, I'm a mess. There we go, that's what I wanted. Luke, what variable are you getting by itself and in which equation? The first one, you're getting y by itself. Okay, not too bad. Not too bad. Charlie, which one are you getting by itself? Y in the second equation? Okay. Now, interestingly enough, both of these guys are going to get the problem right, even though they're both isolating a different variable. Because if you, heck, I mean, you guys, there's 4 different ways to work this, isn't it? I could get x by itself in the first, or x by itself in the second, y by itself in the first, or y by itself in the second. And all 4 of those ways can get me to the right answer. Just don't make any careless mistakes. Someone has been writing on my chalkboard over here. It is what it is. Very profound words. Take you about 1 more minute, fellas. All right, even if you're not finished, let's get cracking on this, okay? Now, if it were me, I would, and this is just personal preference, okay, here, fellas, I would notice in that first equation that there is a common factor of 2 in all 3 terms. And I would go ahead and divide away each term by 2 and get 2x plus y equals 2. You don't have to do that step. That might not even have even dawned on you. But I like that step because it makes the numbers smaller and it's going to make my computations a little bit easier. Okay. Second thing I would do is I would go ahead and get y by itself. Now, very likely a lot of you guys got y by itself in that first, or rather 6x minus y equals 8. Probably added y to both sides, subtracted 8 from both sides. So y equals 6x minus 8. That's the expression that I'm going to substitute in place in the other equation. Now, you did not have to work it this way, but this is the way I'm working it. So the other equation is going to become 2x plus, instead of y, is going to become 2x plus the quantity 6x minus 8 equals 2. And then we just combine like terms. 2x and 6x is 8x. We're going to add 8 to both sides. Divide both sides by 8. And we get 5. What's that? 5/4? Did you guys get 5/4 for your x value? Nice. Okay. Now we're not done, because what do we do next? We take it and we see what y is going to equal. Now I've already got y by itself over here, so I'm going to take that 5/4 and I'm going to plug that in for x. So y is going to equal 6 times 5/4 minus 8. And let's see here. Looks like that's going to be 15 halves minus 16 halves, or -1/2, equals y. My ordered pair would be 5/4 comma -1/2. This is exactly what I was telling you a moment ago, where graphing, you know, we would have pooped the bed on that one. If we had tried graphing, you know, it would have just been a big ugly mess, because these are in between values. This is 1.25 comma -0.5. We would not have successfully known with certainty that that was our solution. Okay. Now, again, this is the first time that you guys have been dealing with a problem like substitute, or with a method like substitution, and I threw one at you where the answer was in fractions. Should we get comfortable dealing with fractions? Everybody's head should be nodding. Yes, absolutely. Okay. Now, what I want you guys to do, our class time is up, so I'm going to let you go. But here's what I'd like for you guys to do a little bit. Okay. If you have not gone on to deltamath.com yet and done your graphing homework, do that graphing homework sometime today. Okay. And then over the weekend, I'm going to give another assignment using substitution. And that'll be some good practice for you guys on there as well. Live Jesus in our hearts. All right. You first 2 rows, y'all can skedaddle. Quinn Page, y'all clear a hole. You guys online, thank you so much. Y'all have a great day. All right, you next couple rows can go. And then you last couple